All right, this is applications of logarithms, and even though we have an exponential here, we're going to be using the logarithm to solve a certain portion or a certain answer. All right, so this is a carbon-14 dating formula for this situation. You see it's 40 grams. We start with 40 grams. And this is our decay constant for our carbon-14. So we have T years, and you have A, which is the amount. So if we're given the amount of carbon-14, we use it for A. If we're given the years, that's our T. So our first one is, what was the amount of carbon-14? So we're looking for our A after 1,000 years. So let me move this over a little bit. So all we have to do is plug it in. And our years is 1,000. So let me pull up my calculator. So here's our calculator. So we have 40, and then E. And on your calculator, when you enter E, usually the exponent shows up. I have to enter it. And it also usually puts a parenthesis. I have to enter it on this one. So negative 0.0001216, and that's not correct. Let's try that again. We need a 1 in there. Okay. Times 1,000. Let me double check it all. Parenthesis, hit enter, and this is going to give us the amount of grams. So 35.4 grams of carbon-14 are left. So after 1,000 years, there's 35.42. So if you were to find 35.42 grams, you would know that the object is 1,000 years old. So let's see how long it'll take to get to 30 grams. So if we have 30 grams, let's write our formula. That means we're given A here. A is 30. So let's plug in 30. And this is our exponential. So let's go back to our exponential equations. Right here. Find one that's like it. And there's the E. So after we put a natural log on each side, this allows us to bring the exponent in front. But there's no number in front here. So in order to get rid of it, you're going to have to divide, just like we did here. So we need to isolate it. We need to isolate this exponential, so let's get rid of that 40. Cancel the zeros, so we get 3/4 equals e to the negative 0.0001216t. Now we can put a natural log on each side. ln, ln. Remember, the ln is going to cancel the e because that makes 1, so it's just going to be our exponent. And then ln of 3/4. So now if we divide this, we can find out what the age is for 30 grams. So let me bring up the calculator. So we have the natural log of 3 divided by 4, close the parenthesis, divided by negative 0.0001216. Supposed to be a 1 in there. There we go. Enter. 2,365 years old. We'll just say 2,365.8. 2,365.8 years old. And that's it. And this is when logarithms get to be used. Alright, so now the main question is, what's the half-life here? So we take the formula again. And remember, 40 is our initial amount. That's what it says, 40 grams. So what's half of 40? 20. So the half-life here is just half of our 40. It's 20. So whatever we have here, cut it in half, and then solve it. So I want you to try to solve this by following exactly the same steps we did here. It's exactly the same setup, just a different number here. It's 20, not 30, to get used to this setup. So hit pause and give it a shot. Alright, so if we divide by 40, we'd get 1/2. And then natural logging both sides. We would get ln of 1/2 equals negative 0.0001216t, because that's going to cancel again and make 1. And then dividing, we get 5,700 years. So what this says is how long it takes to turn 40 into 20, how long it takes to half it. So just to go over this again, if you're given time, the t value, you plug it in, it'll tell you your a. If you're given your a and it's over here, then you have to solve using this format. You know, it's the same each time. So let's try it again now, but this time we're going to use a growth. So if you go back and look at our exponential functions, remember we had decay, that's what we were doing right now. See how it's getting smaller and smaller and smaller? And then we also had growth. And what better thing to use for growth than money? So going back to our compounded interest, we had two formulas. You have this one and this one, and we're going to use the continuous formula. So just to go over the letters, A is the amount, P is our principal, and R is our rate. So to make a formula, we take our principal, we take our rate, turning it into a decimal, and we just have to plug them in. And there we go. Now we have a formula that is very similar to our decay formula, see? Except that's a negative because it's decaying, and that's a positive because it's growing. Okay, so we're given time here, so just like before, we plug it in. Plug it into our calculator. Let me correct that, 475. And that gives us an amount of $5,498.29. So if we invest $5,000 in a 4.75% compounded continuously account, after 2 years, we'll have $5,498.29. A $498.29 profit. Okay, now let's try the reverse. So if we have 7,500, that's our A, how long will it take to reach that? So we're looking for t. And we solve it the same way we did before, which means get rid of the 5,000. So 7,500 divided by 5,000 is 1.5. Go back and put that back in blue. 1.5. Right, and then now we can natural log each side. Just like before, the natural log of e is 1. And then divide it. And that gives us 8.54 years. So it'll take 8.5 years basically to get to $7,500 if we invest 5,000. Alright, so one last. We had half because we're decaying. So if we're growing, it's called doubling. So we want to see how long it'll take for 5,000 to double into 10,000. So that's our new amount here. If it says double, you take your initial amount, which is 5,000, and you double it. If it said triple, you would triple it. If it says half, you half. Which wouldn't work on this one because it's not a half-life. Alright, and now try solving it just like before. Hit pause and give it a shot. And there you have it. So it seems complicated initially, but really there's only two things you're doing. If you plug in for the t, you simplify it. If you plug in for the a, you solve it. In both situations, even if it's growth or decay. Thank you.